Hi, my name is Avi Jenik from Beyond Security, and I will be talking about applying Microsoft SDL verification, the verification phase and its principles to Microsoft Azure. A little bit about Beyond Security and what we do. We specialize in automated security testing tools, and we have a wide range of testing tools from server testing network, websites and products all around security testing, and all in the form of automated tools. We are a member of the Microsoft SDL Pro Network. We've got tools that are a part of that SDL verification phase of the process. We also maintain a website called securityteam.com, a security portal that has a lot of information about security vulnerabilities and how to fix them. And in fact, that's our specialty, is dealing with security vulnerabilities and especially detecting them in a very, very automated way. A little bit about the Microsoft SDL. The SDL is a software security assurance process, and it goes throughout all phases of the development process, from training up to the release and response after that. It's very well documented. There's a lot of helpful white paper and documentation that can help you through the SDL recommendation, and Microsoft provides a lot of free tools and a lot of templates to sort of guide you through the development process. Microsoft provides both templates and free tools to help throughout the complete development lifecycle. And you can see the different tools and different templates here and on the SDL website. One of the leading concepts of the SDL is the fact that the security should be inherent in the process from start to finish in all phases. Of course, my focus here is one phase, the verification phase. There's a few different concepts that are available in the verification phase, things like dynamic analysis, attack surface review. Both are very good processes to implement. I'll be talking more about fuzz testing, which is black box testing. So why is it different? Why is the cloud different, or how does the cloud help security is, I guess, the first question. Well, with Microsoft Azure, we have, or you as the developer, already have an infrastructure that's ready. So you have the server ready for you. The network is available. You just add your code and run on the server, basically. That means that you don't have to secure the server, apply patches, maintain the OS. You don't need to secure the network, and you don't need to install a firewall. All that's taken care for you, and basically you've got that up and running immediately. What you do need to be careful about is your code. You'll be adding your code into this secure infrastructure. There's a famous saying in the security world, your chain is only as strong as your weakest link. In this case, your code is the weakest link. Your code is where attackers will be coming in from, so that is what you want to test and make sure is secure. Black box testing is basically the process of testing the inputs. We're trying to attack the inputs of the application and seeing what happens when we do the attack. And we do that by seeing what happens, what is the output, what is the behavior of the program with the input that we put in. We don't use the source code. In fact, we don't even need the source code for that, which hence the word black box. We're looking at the application from the outside. We only are interested in what is it that, what kind of inputs can we put, and how do we interact with the program. We don't assume a lot of knowledge about the system. All we care about, again, is the protocol, is the input. Fuzz testing and fuzzing are two examples, and in fact two very popular examples of black box testing, and that is what I'll be talking about here. How do we usually do black box testing effectively? As I said, we're not really interested in the source code, and we're not really interested in understanding the product or the application and how it works. That's not to say someone that understands it, like your developers, can't do it. It just means that that information is not necessary. What we are interested in is mapping all the inputs. Attackers will come to attack your server through the inputs that are available to it. And by inputs, I mean inputs in a very, very general sense. That could be any type of file input. It could be configuration files, images. Think about something that reads documents. It could be user inputs. If you've got a web application that accepts input from the user, That's how I will attack you as an attacker. Now, some input fields are very, very obvious. If I've got a login, then username and password are input fields. If I've got a form to fill, then first name, last name, and phone are all input fields, and therefore we use them as what we call as attack vectors. But some input fields are not as clear, not as obvious. And think, for example, about a session cookie. Your application will use that session cookie to identify the session. That goes kind of behind the scenes. That's not something the user sees, but it's something that the user that is user input because it goes through the user's browser. The URL is an input field. Again, you might think that you're supplying that to the user, but the user can modify it and change the URL. So think about all those things as input fields, and in fact, mapping the input is a very important part of black box testing. So think about what is it you have. Do you have IP sockets? Is that a network application that you've developed? Do you use SOAP, RPC? Some very classic, very well-known examples of attacks on user inputs are SQL injection and cross-site scripting. SQL injection is the attack where we alter database queries through the input fields, and the idea here is if the user supplies a username and a password, and those fields, the username and password, go into a database query that checks if the username and password are correct, that basically verifies them, those username and passwords that were entered are input from the user. If I'm an attacker, I would modify my username to try and modify the database query. And there's a lot of information on the internet on SQL injection. I won't go into depth here. Cross-site scripting is a similar attack that works in a little different way. There we alter what the visitor actually sees. We send a visitor a special link that's usually kind of malformed or a little different, and that when that visitor clicks on the link, they'll go to your website, but they'll see something a little different than what you meant to show. And being XSS to see more information about cross-site scripting, those are slightly complicated attacks, not very complicated, but a little complicated. But they are exploited all the time, and there's a lot of weaknesses there. And they all use the same principle that I've just outlined, which is user input. As an attacker, I just change the user input and successfully do those attacks. A little bit about file inputs. File inputs are very, very dangerous because those are things that get to a back-end server, and getting to a back-end server can be very useful for an attacker. Think about an application or a system that secures. You secure your front door very well. You've got a firewall, or you're part of cloud framework that sets up the firewall for you. You've got a very, very secure front end, perhaps. But then your user input and file is one good example for that. Your file will be stored on a back-end server. If I can create an attack that will by a malformed input file, and this is an example for a JPEG vulnerability that affects phones. So if I can create a special JPEG file where when it's processed by the backend, and in this case, it's a Motorola Razr phone, and by that attack, I'll be able to run commands or execute code on your server. That means I've got access to your backend server, even though I don't have access to it directly. Your backend server could be hidden someplace. It might not be accessible to any attacker directly, but I do have an indirect approach to it. Being a back-end server, it might have a lot of useful data for me as an attacker. It could be credit cards, could be passwords, it could be on your internal network. So as attackers, we're very interested in creating those kinds of attacks. Another reason the file input-based attacks are so dangerous is it's very, very hard to defend against them. There's nothing in the middle that will filter out a bad JPEG file. That JPEG file will be just transferred until it reaches the back end, until it's processed. And that means that no amount of, again, firewalls or filtering mechanisms on the way will be able to catch that malformed file until it reaches your code that processes the JPEG, and then it will do the attack. In this case, on the attack on the Razr phone, I don't really care how it is you actually download that JPEG file to your phone via Bluetooth on the web, by an email, as a wallpaper. It doesn't really matter. All I care as an attacker is that you finally display that JPEG on your phone. Once you do, I own your phone. So think about implication on a backend server that you run. Can I send files to it, and can I have it process my files? And if I do, what happens if I generate a malformed file? That's basically what we try to test with black box testing. That's the answer we're trying to answer. When we're in a cloud scenario, we typically don't think a lot about the infrastructure. A lot of the network and the server security is already done, as I said, and the developer, sometimes developers neglect the security aspects of it because they think, well, I've got systems that were set up for me, and they're available on demand. They're secure. I shouldn't really worry about security on them. Well, that's true on the network, on the server level. It's not true on the code level. Code is what you put on it, and that's your responsibility, and you have to make sure that that code is secure. Otherwise, you're introducing the weakness yourself. An IIS server on the internet as part of the cloud network is a very secure machine. Once you add your own code, this is where the vulnerabilities will lie. As I said, the first and important step of black box testing is mapping the inputs. The second is, once you did map your inputs, determine what your protocols are. And when I use protocol, I mean that in a very, very broad sense. Protocols are essentially the language that your applications talk. Those could be network protocols, and any RFC-based or anything that's based on spec. You want to test, you want to make sure that your network applications actually correspond to the RFC. But remember, what we're checking here is not, we're not doing quality assurance. We're not really checking that they conform to the RFC in a good way. We're not in a security verification phase. We're not interested to know if we send a valid RFC request, do we get a valid response? That's a job for the QA guys. What we want to know is what happens if we send something that's just a little different than the RFC, just slightly malformed. If we send something that's really close to your spec but a little bit different, can we generate an attack? Can we trigger an exception? Can we, and that could be either an attempt to do a denial of service attack or to execute code. And keep in mind, those two are very, very close together. A lot of the denial of service attacks where we actually crash the application, what really happens behind the scenes is your application tries to access a memory address that it shouldn't, and then it crashes. As an attacker, if I can control the memory address where it tries to reach, instead of crashing it, what I can do is I can have it either execute code or load some data into memory, some things that you didn't plan to do as the developer. So network protocols are pretty obvious. File-based protocols or file formats are also important, and you need to determine what are the protocols that you accept as valid file formats, and those could be, again, either predefined file formats like GIF, JPEG, doc, or it could be something that you invented and has a spec. But again, we're trying to check what happens if we send something that's just a little outside the spec, just a little bit different. Once we've mapped the inputs and then we define the protocols, we need to start fuzzing. And a good fuzzing framework will have those two components. One is the actual fuzzer, the generator, something that generates the attacks. If it's a network-based fuzzing, then we'll generate those attacks over the network, connect to your application, and send our input to it. If it's a file-based attack, then we'll be generating a lot of files, and then you'll be loading those files with your application. But of course, the second thing is monitor for exceptions. We need to know if you were successful, and that's very application specific. One of the tools that we offer is a fuzzing framework called bstorm. bstorm has a built-in fuzzing framework for many network protocols and file formats, and it has a Windows monitor that monitors Windows applications for exceptions, applications or services. But you could write your own monitor, and in fact, that's a very effective way to monitor your application, because you're in a much better position to know what are bad things that your program can do. So you can monitor the log, you can monitor what type of files are being accessed, and you can define what exceptions actually mean, as long as you monitor. And the goal here is, first of all, to know that something bad happened, but second of all, to understand where it happened and what was the specific request that caused it to fail. An important thing to understand that this thing should be as automated as possible. Fuzzing as a one-time thing is better than nothing, but not a lot better than nothing. What the SDL is about is implementing the full process of this security development lifecycle all across the product all the time. So if you've got an automated framework for black box testing, that would mean, and this is very similar to how you should do QA, that means whenever a new version comes out of your product, you're able to automatically test it. Another benefit of automatically testing is the fact that you can do it over a long period of time. If I was to try and test malformed JPEG files, I can easily reach just over a million, probably close to 2 million different JPEG files that are malformed and I need to test for. Loading 2 million JPEG files may take a while. If I have an automated system to do that, then I can do it over a few days, a week, 2 weeks, a month, and it doesn't really matter because it's automated. So automation is really key in effectively doing black box testing. Resources to help you are, of course, the SDL page or portal on the Microsoft website. There's an excellent white paper that discusses the implementation of the Microsoft SDL, and we have sort of a white paper of our own on the Beyond Security website that talks about bstorm and how that fits in the SDL. If you're interested in fuzzing, in automated verification tool in general, then here are 3 really good tools by Microsoft that are available free from the Microsoft website: BeanScope, MiniFuzz, and Regis Fuzzer. And I really encourage you to try them out and give them a spin. There are also commercial tools that do that, and one of them is bstorm. bstorm has a free trial version available on our website, and you can go and download it and try to do a little bit of network fuzzing and file fuzzing and see how that affects your application. As I said, the most important thing is to integrate that into your application development lifecycle. Thank you for your time and for listening to this talk. I'm available on the web, and you can visit our website in the Microsoft SDL website and contact either us or Microsoft for more information about the SDL and the verification phase of the SDL, and of course how that's linked to the cloud infrastructure and Azure. Thank you very much.